Let us wait for 3 more minutes. Let us see if anyone is joining. Then we can start. Okay, let us start. Good evening. Uh, my name is Rakesh. I was a doctoral student at IIT Bombay. So, I'll be taking a tutorial class on principles of casting, which was taught by Professor Pikeja from IIT Turkey. So, this is the fourth session. In this session, during this week, like this is the session related to the session week of fifth week. So there are some topics considering the riser design, mostly focused on riser design, a little bit of solidification analysis. So I'll be teaching, I'll be solving some of the numericals as well as some of the simple topics while solving these theoretical as well as numerical questions. So let us start with solidification analysis. So you can take some 1 2 minutes to read the question, then I will answer. Then you can either put your answer in the chat box or you can directly unmute and speak. Then we can discuss about the question. So you can either keep the solution in the chat box or you can directly unmute and speak. Okay. Someone is saying option B. So any other solutions? Let me read. So this is the question regarding this riser, the basic fundamentals regarding the riser. So the first option is it must have sufficient volume as it should be the first part of the casting to freeze. So basically riser is the last part of the casting to be solidified because it has to supply the liquid to the casting to avoid any shrinkage. So it is not the first, it is the last one. This option is wrong. So which will so I can eliminate all ABC options since it is considering first option. Option D is the correct one, but let us go through the other options as well. So it must completely cover the sectional thickness that requires feeding. Yeah, this is true. So keeping in mind the shrinkages should not occur. Then the third option, it should be so designated that it establishes and affect temperature gradients within the casting so that the later solidifies directionally towards the result. Yeah, this is also the true one. So it is like if we have a casting and you just kept a riser on the top, so it should be designed in such a way that the solidification should occur, should come in from the all the sides of the casting and progress towards the riser, so that if there is any shrinkage happening, the riser will be in a position to supply the compensated liquid to the casting part. So the solidification should happen towards the riser. So that is also the correct option. So 2 and 3 are the correct ones. So option D is the correct one in this case. Okay. Okay then. If you have any doubts, you can directly ask or you can put in the chat. So let us move to the next question regarding the solidification analysis in casting. So any answers?
A.
D. Okay. So let's see. For the solidification curve, contraction occurs during these processes, that is A to B, B to C, and C to D are done as. So this is simple. This is liquidus. This is solidus curve. So this will be the liquid contraction initially, that is A to B, then followed by the solidification contraction, and finally it is the solid contraction. So this is where we are having this solidification. So option A is the correct one. So can anyone tell me what? So here we have temperature as time. Is this for metals or like pure metals or alloys? Like I'm asking regarding this curve. Nice. Yeah. So this is regarding the alloys that you can identify by this solidification curve. If it has any slope, so that represent it has a freezing range. So if you find a constant line, so it is representing a metal, pure metal. Let us move to the next question regarding the same. Okay. Yeah,
Option D.
that is the correct option. Yeah. So any other answers?
Option D.
Yeah. Okay. So in general, the liquid shrinkage as well as the solidification shrinkage is compensated by the riser, whereas this is by the pattern. So that is what the next question is. So option B is the correct in this case. So this is what the next question is about. So generally this C and D, which is the solid shrinkage, is compensated by the pattern. That is also nothing but the shrinkage allowance. Okay. Let us move to the next question. So what is the answer for this? The purpose of chaplets? Support pattern. Why you need a pair support for a pattern? What is the purpose of chaplets? Any other? Yes. So basically chaplets are used to support the cores. So we have these like this naming. So one is core, the other one is chaplets, then chill, then strainer, and so on. So basically, core is the thing that we use to produce hollow cavities, any cavity inside a casting. Chaplets are the things that we use to support the core. Uh, so if you have any buoyancy force that is happening on the core, it might get lifted, right, due to that force of buoyancy. So we need to support the core. We need to avoid that. So that is where we are using these chaplets. Then chill is used to, you know, there are very bigger castings, and so risers are placed according to that. But there is a certain situation where riser is needed, but for a small amount of length. So in that case, we can use chill, as well as we can use chill for directional solidification. If you want to start the solidification from certain point in a casting, we can use chill. So main purpose of chill is to induce directional solidification from that point. It is nothing but a solid metallic block, so that it has more heat loss from that. Then strainer we use in the entry of the sprue in order to separate any, you know, foreign particles or any slags or intrusions from the stop itself, so that it cannot enter into the casting. So these are the some of the typical names that we use in casting. So let's just move to, so we'll do some of the numericals. So most of this week is about the numericals only. So let us spend some time on these things. So anyone with the answer? Just a straightforward numerical. Anyone with the answer? Or shall I discuss? Okay. So in this, so this is simple, and this is very useful thing when you are designing any component which is operating at very high temperature. So in this case, So we have two types of contractions. One is this solidification shrinkage, and the other is a solid contraction, which is 4 and 6% respectively. So why this is happening is, if you can check the density of aluminum in liquid state as well as density of, for example, I took here aluminum, similarly aluminum in solid state. So let me quickly see the density values. So it is like 2357 gram per cc. The other is 2699 gram per cc. So what I want to indicate here is, you see the density differences. So we have a density, more density in solid form when compared to the liquid. So this is the way, if you see density is equal to mass by volume, since mass cannot change. So volume is equal to mass by density. If density is increasing, so that means volume should decrease, right? Since mass is conserved, so we cannot change. So we have an option D is, okay, let us see. So we have volume decreasing finally when it converts from liquid to solid. So we have some contraction in this case. This is the reason behind the contraction. So because of the increase in density, then we have two types of here. They have given only solidification shrinkage as well as solid shrinkage as 4% and 6%. So since it is a cube casting, it is very easy. So we know the volume, actual volume is 50 mm cube, 50 into 50 into 50. I wrote 50 cube. Okay. Then we have a solidification shrinkage of, so let me write S1 is, we have 4%. So that is nothing but we are left with 96% of the actual casting. Then in second shrinkage, we have 6% shrinkage. So we are left with 94% of casting, which is left finally. So we need to take this from the original volume. So actual volume is nothing but initial volume, that is 50 multiplied by the S1, that is 96%, multiplied by the S2, that is nothing but 94%. This is 112800, and this is in centimeter cube. Sorry, this is in mm cube. And if you want to get the side, let me denote with A. Capital A is the slide, that is nothing. You need to take this cube. So you will end up with 48.317 mm. So this is the correct answer. It is nothing but option A. Okay. So we need to multiply for the whole volume. So one practical example I would like to say. So For example, you have a rectangular, say some coir plate. Okay, we have a rectangular plate like this, and inside it we have one more with a very small clearances. We have one more object. So I am just showing you the front view. So if you see actually, so this is the casting, and we have the actual thing inside, and it is moving actually. Okay. So on the top of this we have some object, and actually it has a movement, up and down movement, and it is operating at very high temperature, say some around 700 degrees Celsius. Okay, so this is a typical example for a directional solidification setup. So basically we will have a heater unit here. So we will completely melt the liquid and we slowly cool it down. Okay, and we have these tolerances, very close tolerances. So what happens? This is not only in direction solidification. Any setup which is having some tolerances. If there are two objects which are having some relative motions, and they have some tolerance, that is, so this tolerance should be taken care, keeping in mind this solid contraction. So many people generally ignore this value. They just do random clearances so that it maintains. So they make sure that even it has good amount of contraction. So what happens for this plate, if it contracts, so this size of this, whatever having this size, will decrease. So the object, whatever is moving, it will get stuck in between uh, this plate. So we should take care of this solid contraction if there is relative motion. So this could be one actual application. So this relative motion, the tolerance is depend on this solid contraction. Okay. So that is how you need to get this tolerance value from this. So in this case, we have 96, some 6% solid shrinkage. So that is, if you take 50 cube multiplied by 94 by 100, and if you take cube root of this, you will get some length. So that is the length you have to take here in order to avoid this type of shrinkages. Okay, that is the like practical example I can say. Okay. Then next, let us move to the next question. So in this case, 48.332 is the correct option. So let us move to the next question. So this is regarding the freezing ratio calculations. Spend some time, and if you are familiar with this shape factor calculations for different types of things, then it will be easier to answer this question. So I will give a hint for these freezing ratios. Surface area by volume of the casting divided by surface area by volume of the riser. So that is the freezing ratio you need to find. So any options, any answers? So straight away you can delete two options in this case. I'll wait for 1 more minute, then I will discuss. Okay, let me discuss then. So basically, I have given the formula. This is the freezing ratio formula. So initially we have everything. We have the dimensions of the casting, 30 into 20 into 5 centimeters. So from that, initially let us take this and later we'll discuss the razor design. So initially surface area of the casting divided the volume of the casting. So surface of the casting will be 2 times, so 30 into 20 plus 20 into 5 plus 5 into 30. So this is the surface area. Divide the volume. It is nothing but 30 into 20 into 5. So we get 1700 divided by 3000. So we got 17 divided by 30. Okay. Then now we need to calculate for this side riser. So it's a cylindrical shape with height and diameter both equal to d, and both the faces are contributing toward the heat loss. So if you remember this shape factor derivation, it will be easy. So basically, if you do, it will become d by 6. But let me calculate here itself. Similarly, for surface area by volume of the riser. So surface area of the riser will be 2 times pi by 4 d square. Since so side riser is nothing but it will be like this. So both this surface and this surface, S1 and S2, both will contribute to heat loss as given, then S3. So this S1 and S2 are both are equal, 2 times pi over d square. Then the later surface area, that is nothing but pi dh. H is here equal, so we write pi d square. So divided by volume of the casting, that is nothing but pi by 4 d square h. That is pi by 4 d cube, I can say. So this is not d by 6 actually. This that is for volume by area, surface area, that d by 6. So you will end up with uh, so pi d square, pi d square, pi d square, 2's. So on the numerator we have 1 by 2 plus 1 divided by, in the numerator we have d by 4. So we'll get 3 by 2 by d by 4. 6 by d. Okay, so this is equation 1 and this is equation 2. Inverse we got because since we are taking surface area to volume ratio. So generally it is, we remember as d by 6. That is nothing but modulus, if you remember that modulus method. So now it is simply a freezing ratio is nothing but 1 divided by 2, that is 17 by 30, so divided by 6 by d. So we got 17d by 180. So straight away we can cancel out this C and D option. Then we are left with only A and B. So if you take this 17 by 180, so it will come near 0.094 D. Okay. So and if you take 8 by 75, it is around zero point 0.1 and zero point 0.1 D. And if you take 4 by 75, it is 0.05 D. Okay. So this is by simple calculations they have given here 80 by 75. If you assume this 3 5 is 15, something like that, it will come. So option A is the correct one in this case, since it is near to 0.1 D. Okay. If you have any doubts, you can spend some more time also. So in this case, if you remember for cylindrical side riser where H is equal to D, the surface area to volume ratio or volume to surface ratio is D by 6. And this D by 6 is same for sphere, that is volume to surface area ratio. For sphere and cylindrical cylinder where H is equal to diameter, also equal to cube of side D. So d by 6, d by 6, d by 6. If you remember that, we can avoid some calculations. This one step we can remember, we can directly answer this question. Okay. So any doubts? Okay. So do this question. So you need to draw the diagram for this question, so it will be easy to answer. Please do. I'll come in meanwhile. I will answer after waiting for 1 or 2 minutes. So any answers? Okay. So the shape factor for casting in the form of annular cylinder of outside diameter 30 centimeters and inside diameter of 20 centimeters and a height of 30 centimeters. Given correction factor k is equal to 1. So you need to draw. Okay. Assume this as a cylinder. Okay, this is an annular cylinder. So we have internal diameter of 20 and external diameter of 30, and we have a height of 30. Okay, so now we can easily find the thickness, that is nothing but 5 centimeters. Okay, so now we need to see. So this correction factor is nothing but, if you remember the table of the correction factor, I think I can show you. So this is the correction factor. If it the core diameter, so the inner diameter is equal to t, then we have 1.14. If it is 4 times t, it is 2 times t. We have different correction factors, but in this case they have given in your question, in question itself, that is k is equal to 1. So we don't need to bother about anything, we can directly go ahead. So this correction factor will be multiplied for this thickness direction. So here it is 5, so 5 into 1 is 5 itself. Suppose it is nothing but some 1.5, 1.2, we have to multiply that to this thickness. So then shape factor, remember, that is length plus width by thickness, that is the shape factor. So in this, length is nothing but the height, that is 30, plus width, if you see, so we have 30, and we have this, we have to see this direction. So it is nothing but 2 pi, 2 pi r, you can say, that is nothing but r pi d, you can say pi times 30, you can take r 30 pi. So that is nothing but the circumference of that outer part divided by thickness, that is 5. So I am getting a value of 20.485. So anyone getting other solutions? So something to do with the weight calculations. So option A is the correct one in this case. Okay, something to adjust this width value, then you will get a approximate value. So in this case, it is 21.77. So any other solutions you are getting? Or else we can move to the next question. So I will discuss more on that correction factor. One numerical is there, then you'll get a complete picture of that question.
Sir, by increasing the degree of superheat, we can increase the fluidity.
Yeah, yeah, that is the correct option. So by increasing the superheat, we can easily get the fluidity increased. Or decrease in pouring weight is the wrong option. Increase in thermal conductivity is also wrong, and increase in the sand grain stretch is also wrong. So the correct option is increase in the degree of superheat. Okay. So I want to add some more details in this question. So this width, we have to take the average of pi d average. That is nothing but 5 into 30 plus 20 by 2. So it will come as 25 pi. If you include that, you will get the correct answer. It is nothing but 21.77. Okay, that is what I missed earlier. So let us move to the next question. Yeah, go ahead.
Sir, it is first one only that chills increase the cooling rate.
Yeah, yeah, correct,
Yes, because chills are used as a heat sink.
correct. Yeah, that is the correct option. So, so, so it doesn't have any to do with the central line feeding resistance. It is just to increase the cooling rate. Also, generally we use for direction solidification also for this. Or instead of progressive solidification, we can induce a solidification since it uh, extracts heat from the casting itself. So option A is the correct one. Any doubts? Else we can move to the next question. So if you remember that Keynes formula, it is the straightforward question. And this is the first method of designing razor. So we have around three to four methods: Keynes method, then we have modulus method, then we have NRL method, and some shape factor method and other. NRL or shape factor and some other methods. So here size means diameter of the riser. So I will give the formula for this Keynes method. So capital H is equal to pi by minus b plus c. So if anyone remembers what is x and what is y. So this is just a plot. If you see, the plot will be like this. So when you we have to be in this region, that is zone casting, and here we have shrinkages. This formula has come from this, and A, B, C are constants given in the question itself. Then we have X is nothing but the freezing ratio. Then Y is nothing but volume of riser by volume of casting. Now we can go ahead and solve. So how much D? Anyone with the answer? So this is the formula you need to remember regarding the Keynes. X is equal to A by Y minus B plus C, and also this X and Y coefficients. And this Y and this X will change for NRL method. That's it. The rest will be the same. So the Y will change for the NRL method. Okay. Okay, I will start. So basically, we need to calculate freezing ratios initially. So since this is the formula for the Keynes equation, so freezing ratio X is, so we have area to volume of the casting, surface area, that is, divided by area of the volume casting of riser. So let me calculate the first one, that is A surface by volume of the cast. So 25 into 25 into 5. So we have 2 times 25 into 25 plus 25 into 5 plus 5 into 25. That is the surface area. divided by volume is 25 into 25 into 5. Then similarly we can calculate the same for riser. So it's a height equal to diameter silicon riser. So I am not calculating here. I know the value, that is nothing but 6 by d, or else you can directly do. Since here it is not provided side riser, so we generally take the top riser, that is nothing but the way for d square. Only one surface is transferring the heat by dh divided by d square h. Here h is equal to d, so pi d square, pi d square, pi d square cancel. So we are left with 1 by 4 plus 1 divided by d by 4. So that is nothing but 5 by d. Okay. And if you do the same for this cast, so we have 1750 divided by 625. 5 is 3125. So this is 0.56. So if therefore x value is 0.56 divided by 5 by d. So that is nothing but 0.112 times d. So similarly, if you do y, so volume of the riser, so pi by 4 d cube. Then we have the volume of the casting, that is 3125. So we have 2.5 into 10 raised to the power of minus 4 d cube. So we have x and y both the values. Just by substituting these x and y values, you will end up with a, some equation. Uh, so I will just write that. So we have x is okay, and we have x is equal to a by y minus b plus c, and we have the values of a, b, c. A is 0.1, b is 0.03 plus c is 1. So if we substitute here, we will get 0.112 times d is equal to 0.1 divided by 2.5 times d cube minus 0.03 plus 1. Okay. So now if you rearrange this term, you will get some equation. So that you need to solve by trial and error method, like keeping d value is equal to 1 and seeing the value of that function. Say this is some f of d. See if the f of d value is going towards 0, then you can go take a larger value, say some 5, and test the f of d value. Take the value of 10. So you can take in step of 5 in tips of t, and then you can see 0 value. Suppose if you are getting here some, say some 5, f of d are getting some 1, so you are closing towards 0. And in some value, if you are getting again increasing the value or decreasing the value, so you need to see that the function approaches 0, so that you will get the correct answer. So if you do that trial and error method, you will end up with getting ds 12 centimeters in this case. So please try once this trial and error method. So if you keep value of 12, you will end up satisfy that equation. Okay. Or else we have this Keynes method. So right now I don't have the chart, but yeah, here I have chart. So in this chart, you can see that freezing ratio, but here D is unknown in this case. So if you know that D also, so we can just match the x ordinate corresponding y. You can take 0.4. From that we can calculate the razor volume. So I'll discuss that in a moment. So this is how you calculate using Keynes method, provided all the constraints and all the volumes of the casting. So I'll move to the next question. So this will be done using the charts that are provided here. So if you have any doubt, you can ask. I will wait for 2 minutes, then I will discuss. This is that shape factor method, or we also call this as NRL method. So just this y value will change. Previously we took the y is nothing but volume of razor by volume casting, but here it is y is nothing but L plus W by T. Sorry, the x value. So x-axis if you see length plus width by thickness. That's the only freezing ratio is replaced by this value, by the shape factor. So any answers? So this is the mixed question. One is calculating the razor design. The other is calculating the compensation. So in this case, we call it as appendages. So these are nothing but suppose if you have a casting, I will show the diagram itself. There is one diagram. So this is these are called the appendages. The four legs here they are showing, which are the extensions of this casting. Okay, so we have different formulas for calculating the shrinkage at the riser volume for appendages as well as the casting. Okay, so in this question we have that appendage value as cross section of 1 square by 4 long, 4 inches long. So 1 inches by 1 inches cross section and 4 inches long. So this comes under you can say bar. Okay, it's the bar feeding the plate. So we have different things. So bar, plate, or bar feeding, bar or plate feeding, anyone in between. So we can classify this according to the thickness values. If the length by width thickness is greater than 4 times the thickness, then we call as a plate. Or if the length by width thickness is less than 3 times the thickness, then it is called bar. So here we take it as a bar. So now we have to calculate this thickness of the parasitic volume by thickness of the parent. Sorry, thickness of the parasitic or appendages. That's what this is also called as parasitic because it was extension to the main casting part by thickness of the parent. If we get that value, we can get the percentage of parasitic volume. So this volume is added to the so suppose if you get value of some value b in this case and some value of a in this case, we should take the addition of these two values as riser volume. Okay, so let me calculate. First we have plate as 5 times 10 times 2, then we can easily get riser volume by, so we have, so in the first case L plus W by T is equal to, we have length or the highest dimension we can take, that is 10, width is 5 divided by thickness is 2, that is 15 by 2, that is 7.5. Okay, so at 7.5 we have to, since we are having two curves, we have to take the value at the intermediate curve. Okay, so now we have 7.5, it should be around some here, say take the value here. Okay, some I'm just taking arbitrarily, so this is 7.5, corresponding is, say I have some 0.5. Okay, so corresponding to 7.5 I have volume of riser by volume casting key as 0.5, so that implies volume of riser is 50% of volume of casting. So 0.5 into 5 times 10 times 2, 50 times 2, that is 100, that is nothing but 50 inch cube. That is nothing but A value. Okay, now I need to calculate the volume of these parasitic things. So that is nothing but, here also we find the this thickness of parasitic by thickness of the parent. So in this case we have thickness as, since nothing is mentioned, we'll take 1. So thickness we can take as 1 in this case, divided by thickness of the parent. Parent thickness is 2, that is nothing but 0.5. So corresponding to 0.5, so this is, so corresponding to 0.5, I will extend these lines. So don't need to worry about the questions, because in exam they will give the exact question, exact value, so you can calculate. So it is matching exactly at 80. So percentage of parasitic volume is 80%. So that is nothing but V razor is 80% of, that is nothing, 0.8 times the volume of this extinctions or the parasites. That is nothing but 1 times 4. That is nothing but 3.2 I am getting. Okay, 3.2 inch cube. So the volume of the, so in thickness, so the volume required to compensate these extensions is 3.2 cube inches cube. So the total volume of the razor will be 50 plus 3.2, that is 53.2 inch cube. Okay, So the final answer is 53.2 inch cube. Okay. So any questions in this? You can speak or you can write in the chat box if you have any doubts. Or else, okay. Let's move to the next question. Anyone with the answer? So I have also explained this question earlier. So we just have to multiply this correction factor to the thickness. So bushing is nothing but annular cylinder. So I will wait for 1 more minute, then I will discuss. Okay. So this question can be easily solved by drawing the diagram for this. So let me draw the diagram. So we have an annular cylinder. Pushing is nothing but an annular cylinder in this case, and this correction factor arrives only in case of these cylinders, annular cylinders, because we have a core. I will explain this. And then we, at the center we'll be having this core, right? So this core, so there will be a less amount of heat loss in this case because it is enclosed inside compared to the plate. Suppose same surface volume, surface area, if I keep in terms of plate, so it will have more heat loss compared to this. That is the reason we add some correction factor to the thickness. Okay, so now let me calculate the thickness of, let me calculate the thickness in this case. So we have outer diameter 12 inches and inner diameter 4. So we have 12 minus 4, that is 8. 8 by 2 is 4. So we have thickness as 4 in this case. So which is exactly, so this core diameter is equal to the thickness. So we have a correction factor of 1.14. So the actual thickness is 1.14 times the original thickness, that is 1.14 multiplied by thickness is 4. So we have 4.56 inches. So that's it. Everything remains same except this case. So now, in order to calculate volume of the riser, so we have to calculate the shape factor. That is length plus width by thickness. Shape factor is, so now width is pi into d average. That is pi into d average in this case is 12 plus 4 by 2. So that is nothing but 16 by 2. That is 8 pi. So we have shape factor is, length is nothing but the height, that is 12 inches, plus width is 8 pi divided by the corrected shape thickness. So we have 8.14. So in this, so we got the shape factor. Now we have to go to this diagram. So we have to see 8.14 somewhere here. So corresponding to that value, so we have two curves. So we have to take the middle curve, middle one in between. So we will be around some 0.5. Okay. So we got VR, the volume of the razor by volume of casting is 0.5. That is nothing but 50%. So volume of the razor is 0.5 into area of this, sorry, volume of this thing. That is nothing but, so this is nothing but a plate, or you can easily calculate. So that is, the height is 12 multiplied by pi by 4, outer diameter square, that is 12 square, minus inner diameter square, that is 4 square. So if you do this, you will get the volume of the casting. So I'm getting 603.18 inch cube. Okay. Volume of the razor. Okay, this is how you can solve this type of questions. So this is applicable only for this type of structures, this annular. So in this case, I took a cylindrical. Instead, you can take a rectangular, similar thing, rectangular with a central core. Okay, you can apply the similar thing because the scenario is same. Okay, any doubt you can ask, or else we can move to the next question. Okay, so let us move to some other question. So you already know about the Keynes method. That is x is equal to a by minus b plus c, and this x is just the freezing ratio, that is a surface area by volume of the casting divided by a surface area the volume of the riser, and y is nothing but volume of riser by volume of casting. And in using shape factor method, we have x is L plus W by T, This is what he given here. And then so in the option C, we just have to add 3% extra to compensate solidification. But still we don't need to add solidification shrinkage. Sorry, we have to add solidification shrinkage for volume. Based upon the difficulties, we have number of methods. One is Keynes method, one is shape factor method, one is modulus method. So calculating these freezing ratios or volume for intricate shapes is it's sort of difficult. That's where we go for shape factor method. The different methods have evolved. So let me start. Yeah, first, I will calculate using the Keynes method. Okay. So we have casting 25 centimeters by 12.5 centimeters by 5 centimeters, and we have A value as zero point 0.1, B as zero point 0, and C as 1, and then riser is side riser with diameter is equal to height. So if you remember, A surface area by volume of the riser is 6 by D. Okay, so X is A surface area by volume of the casting divided by A surface area by volume of the riser. So A surface by volume of the casting is volume is this, and then surface area is okay. So 0.64. So therefore X is nothing but 0.106 D. This is equation 1. Then Y is nothing but volume of the riser, that is I d cube by 4 divided by volume of the casting. That is 5.04 into 10 power minus 4 d cube. So this is equation 2. So from 1 and 2, if you substitute in this formula, that is X is equal to A by Y minus V plus C, and if you do trial and error method, you will get this value of the dimension, that is nothing but T. So this is the Keynes, in short, Keynes method. Okay. Then let me do same thing for shape factor method. So in this case, just the axis change, that is L plus W by 2, W by 2 of the casting. Okay. So we have length of the casting, that is 25 plus 12.5 divided by 5, that is 7.5. So and y we have, then we use the same formula, that is x is equal to a by pi minus b plus c. Just we have this x value as 7.5. That's the difference. The rest are the same. Then finally, they are also asking us to include this volumetric shrinkage of the solidification. So that is not 3 times the shrinkage concentration alone. So nothing but so we have 3% shrinkage. So we have to take a 3% multiplied by 3 times since it was given. So total 9% extra we need to get. So if we get volume of razor, say x, say centimeter cube, actual volume, that is P prime, is x into 1.09 plus by 100, and we can just write 1.09 centimeter cube. This is the actual volume considering the solidification shrinkage as well. Okay, so this is how we need to solve for this Keynes method as well as the shape factor method. So these are sort of descriptive but useful as well in numerical questions also. So let me quickly go through the other questions. So this is also the same model but different approach. So instead of having, see, previously I have solved one question with single appendage or the single parasitic volume, but in this case we have 4 times. So we just have to add these 4, calculate for 1, multiply by 4, we'll get the appendages for 4. Add this to actual volume of the razor. So you can try this question. So this NRL is one more name for shape factor. Both are same. So for this you need diagram. So this diagram you need. I will tell you. Just calculate, then I will tell you. So according to the shape factor, you need to select the volume of the razor by volume of the casting ratio. So let me do along with you. So let me do for the first one. So in this shape factor, 1 is equal to 40 plus 40 by 8, that is 80 by 8, that is nothing but 10. Similarly, shape factor for 2 is what 7.25. Okay. So now we have to look into this one. One is 8. Cannot say exactly 8, but yeah, that is true. This is 8. Okay. So if you join these two, you will get around zero point 0.4. The other one is 7.25, says a little bit here. So which is coming around some zero point 0.5. Okay. So for this, volume of the reservoir, volume of the casting is 0.4. For this, volume of the reservoir, volume casting is 0.5. Okay, the rest will be similar. So in this case, volume of the razor is nothing but zero point 0.4 into, see this dimension, that is 40 into 40 into 8. So we'll get 5120. Similarly, here also volume of the razor is zero point 0.5 times 25 into 4 into 4. So we end up getting 200. So now volume of razor is 5120 plus, so total is 5120 plus, we have 4 appendages, so 4 times 200, that is 5920, okay, centimeter cube. So now we have given C with the height to diameter ratio. So h to t ratio is 0.5, or d is equal to 2 times h. Okay, so we can get the volume, that is, so nothing is specified, then we have to take the actual volume. So volume of the razor is pi by 4 t square. H is nothing but zero point 0.5 times t into, which is equal to 5920. So if you do this, you will get d is 24.7, nothing but 25, 25 centimeters. Okay. So if you have any doubts, you can ask. We are approaching the end of the session. Okay. So any doubt till now, you can ask. Okay, then let's move to the final question. This is the last question. So any answers? So this is a direct question. Just calculate the freezing ratios. Then from the graph you can get the volume of the reservoir and casting. Then you can get, since it's a cube, you can easily get the volume of the casting and the riser. Okay, let me start. So in this, they have given a cylindrical riser of diameter 4.5 inches and height is also 4.5. Height is equal to diameter. Then they are asking whether we can produce a cubical casting of edge 4. So let me take A as the size of the cube, which is 4 inches. So let us see. So this simply, if you can calculate the freezing ratio is nothing but relative ratio between the volume of the casting to the volume of the riser. Yeah. So A surface divided by volume of the casting divided by A surface divided by the volume of the riser. So this is nothing but, so let me, A surface by volume of the casting. So we have area is 4. So we'll get 6 by A for this if you do, or let me do. So area is nothing but 6A square, right? Surface area. So 6 into area is 4 square divided by volume is 4 cube. We'll get 6 by 4, that is nothing but 6 by A. That is 1.5. Similarly, A surface by volume of the riser. So this will be also 6 by D. D is given 4 point inches. 6 by 4.5. So we get 1.33. Okay. Now freezing ratio. From this we get freezing ratio is 1.5 divided by 1.33. So we got 1.125. Okay. So now we focus on the diagram. So we got 1.125. So it will be around here. Okay. And let us match this. So we got around some, so 0.75. Let us take. So V razor is zero point 0.7 times V casting. Okay, for so I am taking at the exactly, so it is like if we come below it is shrinkage, if we come above it is sound casting. So it should be more than, so I am taking that midpoint, that like limit value. So that is nothing but 0.7 times volume of the casting is 4 cube. So which we end up with 44.8 inch cube. So this is from the Keynes method, 44.58. But this is from Keynes. But what is the actual volume of the riser? Pi by 4 d cube, that is pi by 4, 4.5 cube. Since diameter of the casting is riser is given 4.5. So if I do this, I am getting 77.57 centimeter cube. Okay, this is the minimum, 44.8 is the minimum volume required to compensate for the shrinkages. But actual volume that we used is 77.57. So it is well above the limit. Okay, then so it is able to produce the cubical casting of H4 because it's somewhere It is zero point 0.7. So volume of VR by V casting will be somewhere here. Okay, so if, let me do that. 77.57 divided by volume of the casting, that is 4 cube. That is 1.2. So somewhere here it is, which is a sound casting. Okay, so we are able to, yes, that is how we can also verify. It's like a verification thing. So initially it did not follow the case. We just took the random value of d value, and now we are verifying whether it is able to produce a sound casting or not. Okay, any doubts? So this was the last question. If you have any doubts, we can discuss. Okay. Thanks for joining. If you have any doubts, we can discuss. Otherwise, you can leave. We'll meet in the next session again. Any doubts? Sorry. Yeah, if you have any doubts, we can discuss, or we can call it a day. I hope you understand something. Any questions? Yeah, thanks for joining. We'll meet in the next session. So we'll end the session now.